He's going to talk to us on the subject of his recent book, copies of which are available upstairs, thanks to Waterstones who are here and who have brought a few copies with them, so you can buy a copy and get it signed after the talk, but not before.
Yeah.
So, after all, it's a gas.
See if you think it's worth
Mark,
it. Yeah.
go ahead.
Hi, thank you very much for the invite. Yeah, and what I want to talk to you about is gases. They often don't get whole talks themselves often, so hopefully this will be a special thing for all of us. And I wrote a book about them because I thought they're really, they are invisible, most of them. It's kind of weird how many of them are invisible, and they're odourless, and most of them don't taste of anything either. And so they're this kind of invisible substance that surrounds us all. But as I sort of researching the book and writing the book, I realised that they really are our life support system. I mean, not just the air you breathe, giving you the oxygen, but they are responsible for our sense of smell, and that's so important psychologically in terms of our emotional range of interacting with places and people, and loving people, falling in love with them. A lot of smell is really important, and also memory. Like when you lose your sense of smell, you lose that kind of direct evocative moments that pop up from the past, and also it turns out, of course, that a lot of our technologies are based on gases, and they're sort of hidden in society, and I wanted to bring them to the fore. So yeah, that's what it's about, and I wanted to start sort of historically in a way. So fire is a gas technology, obviously. Well, we say that obviously, but our ancestors didn't think that. They thought that fire was a substance, an element, in fact one of the four elements that would make up the whole of the world. So there was fire, air, water and earth. And of course it sort of makes sense because it is such a special thing, fire, and it's hard to how do you understand fire? Like if you haven't got the kind of vocabulary and the chemical understanding of what's going on in the process of fire. And it takes a long time in the history of science to nail down what fire is. And in fact, the phlogiston theory, which is essentially the idea that fire is about something that contains phlogiston and then gets released when it's hot, and then gets absorbed into the air, and then the plants take it from the air, and that's why wood burns. That's why plants burn, but it's why stones don't burn. It's why water doesn't burn, because it can't absorb phlogiston. Not the right theory. Had to wait until the discovery of oxygen, Joseph Priestley, and even then he didn't believe it. He discovered it, but he still stuck to the phlogiston theory because look, it looks like a substance. Very hard to understand. That is an oxidation process that's heating up little particles of carbon that are unconsumed oxidation products, and the glowing hot.
Mark, can I point out, when you jump towards the screen, I'm not sure that people further up the lecture stage can hear.
You can't hear. You can.
Yes, no problem.
You can hear.
Yes, I thought that was cool. Right.
Okay, thanks. Okay, so we've got fire, and then of course, as I was saying, there are these four elements historically, and of course the wind, air, is another one that clearly seems to be an element. And again, it took us a long time to kind of dissect air because it's invisible and a mixture, and actually you need very distinct chemical kind of techniques in order to extract the oxygen and the nitrogen. And then the story of the noble gases, and argon and neon and helium and all those, which we'll get into. But when you don't have those techniques and you don't have that before, the thing that really impresses you about this element as they saw it is not so much that you need it to live, because they didn't really understand that, but it was that it had such force, like storms, like we see them today. Like we talk about these enormous hurricanes that hit the Philippines at the moment. These were just immense, kind of demonstrations of the force of wind, and of course they associate those with gods. And every single culture has a god of air, and of course the Mexican god of the wind is hurricane, right? And that's where we get the word hurricane from. They're often very angry, these gods. For reasons that it's not clear why they're always so angry. But when it's a lovely calm day, there's very few gods that are associated with lovely calm days. But we harnessed, so in the case of fire, that was an elemental kind of process that we harnessed in order to Well, it turns out that fire helped us evolve as humans because, well, it's thought that the growth of the human brain is partly to do with the fact that we conquered fire and managed to cook food, and that made more calories available to our ancestors. So there's a big increase in the brain size when we start eating cooked food. And that kind of makes sense because a lot of food is indigestible if you eat it in its raw state. If you cook it, you're basically pre-digesting it. And so, but in the case of wind was harnessed to allow us to get around the place. And in fact, the whole of the earth was colonized by a few people coming out of Africa and basically being able to travel. And the bits that were connected by the land, they could go on foot, but vast tracts of it had to be tackled with small boats. And this is an ocean-going kayak, which is still in use today. It's Polynesian design, and is thousands of years old in design, and it's incredibly well adapted to being able to travel thousands of miles. And they did travel thousands of miles. And the Polynesians didn't ever develop compasses. That was the Chinese. They didn't develop maps because most of the ocean in the Pacific there's just nothing there. It's just water. It's these tiny dots, right? But they still managed to navigate accurately between them and keep pushing the boundary, and got to Easter Island in the end, which is 5,000 miles on these boats. So it's really extraordinary their ability to do that. And then the other thing that we kind of quite quickly got the hang of is using wind as a power to grind things. So this is a vertical windmill, and it's in Iran. It was Persia, and it's sort of 1,000 years old in terms of its location. Still exists today. It's an incredible thought that those things are so valuable. And yeah, they grind corn, and of course water wheels and windmills in this country. They have a very long history, and now we have wind turbines. And then coming back to ships, it was actually the Chinese who really got going on the big ships, and then in the end Europe caught up and produced some of the bigger ships, sail ships that ever made, and that they really allowed these powers, these sovereign powers, to extend their domains over the whole globe, right? And this is when the first circumnavigation of the whole globe happens by a Spanish team, and most of them die on the way. But there were these epic adventures, colonialization, domination of other people, but it's all wind powered. So when is it that we get a gas technology that really is sort of, in a sense, controllable, not by the elements or controlled by the globe, but by ourselves? And it's really, the first one is really steam power. And there's a guy called Hero, who's a Greek, and he invents the first steam engine. It doesn't work very well, and he's basically using steam as basically a gas jet, so just heating up water in a container, producing steam, and it shoots out the back, and then he gets it to rotate something. It's really inefficient, incredibly inefficient, and it doesn't really take us anywhere. So 1,700 years later, a guy called Thomas Newcomen really, and he's not the first to do it, but he's the first to make money out of it and to really make something workable. And this is the first steam engine, and it's designed to pump water out of mines. And if you can think of the mine being down here, the big problem in this country was that coal would cut down most of the forests by this point. This is 1712, and coal was the fuel of the future for heating and for processing, and manufacturing. But these mines were getting deeper and deeper, and they were filling with water because it rains a lot in the UK. So getting the water out of the mines was really important. They usually used horses, and they just had horses going around in a circle. And Thomas Newcomen was really keen. He's a blacksmith, really keen on getting this to work. And it's basically a cylinder. You can see it here. This is a furnace to heat up the steam, and it gets introduced into the cylinder, and then it's condensed. And why does this work? And Heroes, why do you need a sort of cylinder setup in order to really make steam work? Answer: the real power of steam is in the fact that it goes from being a gas exerting pressure to being having almost zero volume and exerting no pressure when it condenses. So if you can cool it from a gas to a liquid very quickly, you create a partial vacuum, and that isn't the force that brings the cylinder down, it's atmospheric pressure that does it. So this is an atmospheric steam engine. And if that doesn't make sense to you, let me show you. This is a little demo I did at home. So this is a little one of these coffee cans of coffee, and I'm going to show you. I put some steam in it. That's a hot plate there. Hopefully this is going to run. And I've got steam in there now because it's hot, and I just close the lid. Okay, and so now the steam's in there, but it's resisting atmospheric pressure. But then I cooled it, it all condensed, and the atmospheric pressure is now doing that to it.
Oh, wow.
Does that make sense? So just go back. Now you know what's going to happen. You can have a look at it. Like that. There we go. So I have steam. I close the lid, so the steam's got nowhere to go, but the steam is pushing back against atmospheric pressure and keeping the can alive. But as soon as it's a liquid, atmospheric pressure crushes it. And we've got 100 kilometers of air above us, pushing down on us. We've born into it, so we don't notice it. But if you suddenly get rid of it, we would all explode. We are pressure vessels, and so if you go into space and you're exposed to the vacuum of space, you're going to explode. And so that's the power of steam, and that's what Newcomer understood. So that is the engine he made. And so, okay, so you've got the steam engine working, pumping water out of our mine, and then everyone gets excited about it. It's like, but it's a bit boring. Can't we do something more interesting? And so, of course, what you want is a steam car, right? So this is like 1730s, 1740s. 1770, this guy called Cugnot in France, Jean-Pierre Cugnot, he goes, I've done it, I've made the first steam car. So as far as we know, the first steam car in the world, and that's the boiler at the front there. It's introducing the steam into the cylinder there, and you can see there's a chassis and some wheels, and basically the same thing, same idea. You just miniaturize it, and this basically goes up and down, and it has a gear system, and you go places, not very fast. And he sold it to the military. He was, he was selling it into the military, saying, look, you don't need to have loads of horses anymore. They're temperamental. We can get the cannons from A to B with just water and coal. And so they tried it out, and they sort of hated it. And the reason they hated it was it wasn't very fast. It's incredibly heavy. All of this gubbins, at the time they didn't have the right steels and the right kind of valves, and so everything was oversized, overspec'd, in order to make it safe because it's a pressure vessel. So it's very heavy, very unwieldy, very hard to steer. The roads were terrible, they're all full of potholes, and basically would crash all over the place. And then you had to bring all your fuel with you, so it was actually really inefficient. You had to bring the water and the coal. So they abandoned it, and pretty much everyone else abandoned it too. And so the age of the steam car, this is 1770, hadn't happened yet. Just to say, at the same time in the UK, this guy called James Watt is playing around with steam, and he thinks he can make it much more efficient. And he does something quite clever, which he says, if you condense it like I did with that bottle into water, everything gets cold. Then you have to heat the whole thing up again, and that just costs you a lot of energy. But what if you just vent the steam to another cylinder, and that's always cold? That will compress it, still create the partial vacuum, and you have this much more efficient steam engine. You have two cylinders, one's cold, one's hot. And anyway, he basically it's about times 10 more efficient, or 8, depending on who does the calculations. And he starts selling steam engines all over the place to manufacturers, and the factory running on steam engines becomes a thing. And so in the UK, it's sort of the birth of this idea that you can start moving away from manual labour when you're producing things like textiles and clay and all these other things all become steam powered. And so then people go, well, okay, we're trading all over the world, and we've got the sail stuff going as we saw before, but why don't we put a steam engine in a boat? Because then you haven't got the weight problem and you haven't got the road problem. There are no roads, and the weight doesn't matter because you just displace water anyway. And we can now sail anytime, any place. We don't have to wait on the weather. And this was actually turned out to be quite a big deal, not at first for long distance, but for small distances, up rivers particularly. So going up a river, if you're dependent on the direction of the wind, is really hard. But if you're under steam power, brilliant. And if you have both sail and steam, you can sail across the sea, and then when you get close to the thing, you got. Anyway, they loved it. People loved it. But not just that. Like then they realised, oh my God, you can scale this up without any problem. And so you get. Oh no, I haven't got that bit yet. Sorry. Steam. You get steam liners. So eventually, you get a liner so big that you can take 4,000 people. From London to Australia, like non-stop. Unbelievable what they're up to. And they were luxury, like they had first-class luxury ballrooms, running water, just an incredible luxury travel. And this opens up, by the way, the idea that the ordinary person can travel the world. Before this, if you wanted to travel anywhere, you either were royalty or a soldier or a sailor or a fisherman and trader or something, but these were special people, and it was very treacherous and dangerous. Here is basically world tourism happening, and it's all to do with steam. I just want to go back to but in the meantime, the steam car is very much still what everyone wants, but the roads are too bad, and as I said, it's very heavy. So this is a locomotive, and why does the railway win 100 years before the car is invented, a viable car? Why? Because, first of all, you can sort the roads out because you own the roads, you've got rail, and you have steel rail. So all this weight, like 10 tons, 15, 20 tons of thing, it's fine. I mean, not fine, loads of rails broke, but anyway, it's doable. Secondly, when they did it, it was actually to get coal from a mine to the sea, and it was just to. In fact, railways existed way before this, like without steam, like they were horse-drawn, and they were in every mine. They had wooden rails, but if you change the rails to steel, which was getting cheaper, and then you could do that much faster. And then they think, well, we'll put a carriage on for people. I mean, no one's going to want to go in it, are they? Anyway, people loved it. They loved it, and so this is around 1820. You get the birth of the railways. You get sort of people start to do it in Stockwell and Stockton-on-Tees, and then everyone goes for it. Within 20 years of that first railway happening, you have 1 million railway journeys in the UK and everywhere in Europe and everywhere in the globe. Like people it's the future. So railways, there's 100 years of railway being the optimum way of travelling around the country, and loads of people invest. It's very investable because you own the infrastructure and you own the means, and then people pay you. And also, it's inherently democratic because you can't make money unless you've got thousands of people travelling on it, because you put such a big investment to start with. So instead of just the rich being able to travel to the seaside, everyone gets to travel to the seaside. So the holiday is born in the UK and probably across Europe because the steam engines make it a necessity that you have to allow loads of people to travel. And so people had holidays before when they were in a village. They'd never seen more than 10 miles away from them, ever, in their whole lives. Like generations of people would never go over the hill they could see. With the railways, everyone gets to go to a seaside holiday. And all the seaside towns are born, and they all have a tourist trade, and it's all because of steam. It's an incredible thought. And then, of course, I was saying before with the liners. Anyway, steam is like amazing. And it's still with us today. Like 70% of all electricity in the world is generated by steam. It's just hidden away. People don't talk about it. They talk about wind and solar. And everyone's very excited, and that's great. But basically, still, we're a steam civilization. Okay, then I'm doing a little bit of a tour now of some of the gases in the book. I want to talk a bit about laughing gas because it's kind of a different way in which it interacts with society. Whereas steam was like this powerful thing that really released people's desire to travel and to kind of not do so much manual labour or pumping out water and whatever. Laughing gas is a different thing. It's all about pain and how we mitigate pain. Wrong way. Okay. Now this guy called Humphrey Davy here depicted. He's a young guy. He's hired by this guy called Thomas Beddoes. Again, we're talking about sort of 1800s. He's from Cornwall, and the idea of the Pneumatic Institute, which is based in Bristol, is like they have all these airborne respiratory diseases, not least TB, which is killing millions of people worldwide and still does, by the way. And they had no cures. So they had an institute, like his idea, his role was to try and find cures for this. And so they did things like getting patients to breathe cow's breath, because some people had found that milkmaids who had particular cows didn't ever get TB. They were just trying everything out. I'm not kidding. They had cows in the institute and people were breathing the breath. It didn't work. And this is the time when lots of gases are being discovered. Joseph Priestley is around. So Davy, who's an 18-year-old, he's up for inventing something new. He starts playing around with all these gases. He plays around with carbon monoxide and almost kills himself. He does it all himself first. Almost kills himself with carbon monoxide. Then he tries nitrous oxide and has just this incredible experience of just being out of his mind and laughing. And he's in charge of the institute and all these very ill people around. So it's really inappropriate that he should be giggling at them. But he can't help himself. And so he realizes, oh my God, this is incredible stuff. But then he starts having these parties and he gets accused of being a misogynist because women are coming to the institute and he's giving them laughing gas. And so this cartoon is a very important sort of relic of the time, which is like, on the one hand, here's an amazing discovery by someone who's doing experiments. On the other hand, the press have got hold of it, and all they want to do is take the piss out of everyone and belittle them. And so he's depicted as someone who's not a serious scientist, and the people coming are depicted as sort of prostitutes, and so he gets out of the whole thing. He uses laughing gas later in his career. He goes to the Royal Institution, but he sort of doesn't want to really do anything serious with it, which is a pity because he does notice in his diaries one very important point about laughing gas, which is even though you laugh a lot, the other thing is you become insensitive to pain. And that's not true of things like alcohol. Like you can get blind drunk and you will still feel pain. And so if you have to have an amputation, which was happening a lot of the time, or a tooth being out, people would drink whiskey or they'd drink rum in order to numb the pain, but actually it would just make them feel ill and they would still feel the pain. Laughing gas didn't do that, but he didn't take it forward. The other thing that is interesting to note is that other people who were also interested in that didn't take it forward either, because the doctors weren't interested in an anaesthetic. And why? That sounds odd, but the thing is, the doctors at the time thought that pain was a really important part of being cured. So if you didn't, as a woman for instance, if you didn't go through labour and weren't in real pain, the child wouldn't be a good person. So it was really important that women felt pain, those doctors felt. I know. And so everyone basically said, it's not an important observation that it's an anaesthetic. And so what happened is that other people took it up, but they took it up for performance. So it became this big sort of fairground act. And this guy called Samuel Colt in America, he started doing these laughing gas shows where he'd get people up into the audience like this and he'd give them some laughing gas and they'd suddenly become a completely different person. So you get someone who's very proper and and then they'd start larking about and being all funny, and it wasn't an act, they were just on laughing gas. And everyone loved it and everyone paid money, and he made a lot of money, and he then did what he really wanted to do, which was make a new gun, the Colt, the revolver. And that's the gun in every Western, and that's how he got his money to do it. Other people around the world were starting, this is the 1870s, 1880s, other people were starting to experiment on other gases, so ether, so sniffing ether, that's also an anaesthetic that's quite dangerous. And this guy called Simpson, Dr. Simpson, he's in Edinburgh, and he starts every Thursday, he and his mates sniff a new chemical they found, and one day he sniffs chloroform, and he doesn't remember anything until the next morning. They're all passed out, and then he goes, wow, this is pretty good, this could be good. So this could be an anaesthetic, you think. I'll try it on my niece. So he gets his niece in, she collapses and then stands up and then starts singing, and she's an angel. And they think, this is brilliant. Anyway, so he starts using it in his practice, and everyone says, oh, you're an idiot, you're not a proper doctor. This idea of self-experimentation and of being a doctor, this is taken up by Arthur Conan Doyle, and he bases Sherlock Holmes on this figure, a person who is quite radical in the way he approaches life and does strange things, but is also a rationalist and also able to kind of deduct crimes. And in fact, the whole crime world takes chloroform up. Agatha Christie, I mean, for about 50 or 60 years after that, pretty much everyone starts putting chloroform in a rag across someone's mouth if they want to kind of abduct them. And everyone sort of thinks it only takes 5 seconds because none of them have ever tried it. So in the books it's also he put it over his mouth and they became helpless. But of course it takes actually much longer than that. It takes minutes. And so then actual real criminals started doing it, inspired by the books, got it from the pharmacy and started trying to mug people. But they also were surprised that people were still wriggling after 10 seconds. And so there's all these newspaper articles of people trying to find these criminals who are trying to abduct people and rob them using chloroform. Anyway, it's a bit of a mess until Queen Victoria uses chloroform for the birth of Prince Leopold. And suddenly she goes, it's so wonderful, it relieved me of pain, everyone should use it. And because it had the royal seal of approval, it suddenly anaesthetics are okay. Suddenly the medical establishment says, fine. And this is just another picture of the Royal Institution, kind of showing at the time, like how the press viewed these kind of experiments, both as they ridiculed them, they were circus acts, they thought these are not serious people, but at the same time it was changing society, it was changing people's real experience of pain, and of course at the Royal Society they were also discovering loads of new gases. So yeah, it was an exciting time. And now methane's another really interesting gas because it changes everything. It kind of forms what we think of as normal town and city landscape, but it does it in a quite different way. So methane is odourless, colourless, tasteless gas. It's also flammable, as you know, and they start to understand what it is and where it's coming from. They start to realise it's coming out of bogs and is responsible for the will-o'-the-wisp floating lights in kind of woodland at night. And by the way, every culture in the world has a word for will-o'-the-wisp. So like it's a really, and they're usually evil spirits, except in Sweden where they're good. But everywhere else thinks they're evil, and they lure you to your death. But basically, it's methane is bubbling out of the kind of anaerobic digestion of vegetable matter inside a bog, and that then sometimes self-ignites in a way that we still really don't quite understand. But it involves phosphine, it's a miracle thing to witness. But then after a while, people start thinking, well, could we get hold of methane and not just have it as a will-o'-the-wisp, but could we use it on a stick to light our cities? And taming methane is a really interesting story because, again, it sort of mirrors the steam engine development, it mirrors laughing gas. It's sort of early 1800s. People have a go at it, but because it's flammable and because it's hard to control, there's loads of accidents, and it's not really obvious that it would ever succeed. The idea of making methane whole scale in some sort of facility that has to be very close to where you want to ignite it, which is in a city environment, which means that literally in the centre of every city you're going to have a gas making machine, huge one, making gas the size of this building and bigger, in order to supply enough gas for all the roads and all the streets so they can burn when the sun goes down. So it's a big enterprise, and it involves discovering ways to hold gas, airtight, for it not to explode, to be able to meter it. They didn't have any meters at the beginning, so they had to have people called who basically went around. They looked at who was using the gas. So it wasn't just in the streets. Individuals could buy and put it in their houses, and they would look through the window and they would note it down, and that's how you metered it. So people just walked up and down the streets. Why was that viable? It was thought to be very modern, but more than that, it was thought to be a sort of a miracle of enlightenment. Like before this, every city in the world, however fancy, was dark at night and dangerous because it was dark. Like anyone who was up to no good did it at darkness. If you had any thieves, muggers, rapists, they did their business at night. So you didn't go around, if you didn't know what you were doing with yourself, you did not go around at night. And places like London, big cities with big ports, they were especially dangerous. People would just mug you, slit your throat, throw you in the river. No one would ever know. So incredibly dangerous. And they thought, look, if we can light the streets, we basically at a stroke make our city much safer, much more civilized. We'll show the rest of the world. And this is the British Empire now, like trying to assert itself. So although the first street lighting was demonstrated in Paris, the French didn't really take to it. It's a bit pongy at first, unless you can get rid of the sulfurous compounds, and you have to do sort of lime water treatments to do that. But if you get the hang of that, it's not pongy anymore. But you have to get all the piping. You have to be prepared to all the leaks. You have to prepare for the odd explosion. And it turns out we still have the odd explosion now. Like, even though we have all this much more sophisticated technology for monitoring it, there's probably not a week that goes by that somewhere in the world a whole building doesn't explode because of gas has been built up. There's a leak. So it's still quite a tricky one to do. But nevertheless, within 20 years of the first gas lighting being demonstrated in London, every town bigger than 100,000 people in the UK had gas lighting within 20 years. That's how much they wanted it. They wanted to walk around their streets at night and not be in fear. But it was a real sign of like, look at us, look how amazing our town is. So there's kind of competition. And then that means every city, every town had a gasworks. And that's what they look like. So these sort of massive cast iron structures where these things over here, if you've never seen them as you're a young person, I grew up with them, these rise as the gas is produced during the day. So they make the gas during the day, these get bigger and bigger and bigger, they've got the bearings at the bottom of this, and it goes into the ground. You make the gas, and then it gets really full, and during the day, you supply all the streets. So these were everywhere. There was in every town. And you'll see them now as fancy flats often. A lot of them were taken down, sadly. But this is like a really amazing thought. And if you're thinking, well, yeah, but electricity came along 100 years later and blew out the water, you're right. But gas still remained in the system. And why has it remained? Because it became a really very efficient way of heating our homes. So central heating comes in, and that's gas. And it becomes a very good way of having hot water and cooking. Because before that, you had a lot of smoke from coal fires. And actually gas was much cleaner. I mean, it's not clean, but it's much cleaner. So the whole shift away from coal and wood fires in the home to a clean burn, almost completely clean, a gas technology, that whole modern shift, that all starts with wanting to walk around your street in safety. And I wouldn't be doing justice to the problem if I didn't really say there was a massive commercial, that it's all typical Britain actually, to really cotton on to the fact that this would make a lot of money. Not just people buying the gas to light their homes, which they did, and councils buying the gas to show how great their town was and get people to come there, but they worked out that then you could keep the shops open later, and people would buy more. And in particular women. So women would never go out at night because it was very dangerous, and now they could go out at night, and so on. So yeah, I'm just sort of plotting these kind of amazing moments in our history, which we sort of take for granted, these different gases that we've kind of tried to harness. And I'm just wondering, hold on, I'm doing all right for time, aren't I? Hydrogen's another really interesting one, another flammable gas, and hard sort of to pin down. But I think that the story of ballooning is really the one that I found really most appealing. So the ballooning craze starts, in the sort of mid 1700s, and it becomes this thing where once it's proved that you can take to the sky in these balloons, these are daredevil people. I mean, this is not every person, and you can land. Then everyone it's just this thing that everyone wants to be involved with. So basically, no royal occasion in Europe anyway was complete without a balloonist, and they were hot air balloonists. But amazingly, I think this is 1774 or something. 1783. This is a hydrogen balloon. And what they work out with hydrogen is that they can make it quite easily. So you just add iron to sulfuric acid, and sulfuric acid is actually is quite plentiful at the time. Like there's lots of processes sulfuric acid is used in, called vitriol, and so you can get hold of it. So because the balloonists had to travel around the different cities and royal courts. So you turn up at royal court, you're a balloonist, you say, bring me some iron filings and some vitriol. You have your balloon, it came in a cart with a horse. You lay it all out on one of their massive places, and then you start producing hydrogen there and then. You pump it into this balloon until it gets big, and then of course you tie it down, and then when they're ready for the party, you get in it, and you fly above them. And you just hope that no one, is smoking. And they were, what would happen is that they would have to control it, right? So they would fly over the Alps, they'd go into Italy, but then a massive storm would come and they'd get blown out to sea, and no one would ever see them again. I mean, it was really intrepid stuff. But they did it anyway. And I'm really just struck by how brave they must have been. These are the sort of people who, they climb up buildings without any ropes. And these are those same people that we see today, but they're doing it with balloons. The military get hold of this idea and they start thinking, well, this is really brilliant. So it becomes a military technology, and what happens is you can see the vitriol being mixed with the iron filings here, and this is an inflating a hydrogen balloon. This is the Civil War, the American Civil War, and they go up and they can see where everyone the positions are, and they tell the gunners, and then they start sending cannon fire to the place. So they start using this. They go up and down, and of course everyone shoots them, and then they blow up and they die. So it's very dangerous. There's a guy called Zeppelin, who's a German guy, Baron von Zeppelin, and he goes up in one of these American hydrogen balloons in the Civil War. I think he's just an observer at that point, and he thinks, whoa, it could be more than this. This could be the transport of the future. So he has this bee in his bonnet about hydrogen travel. Because hydrogen is so light. See, there's no gas that's as low density as that. It really has a buoyancy. You think helium's, you get a helium balloon, it tugs your arm, and it's very impressive. Hydrogen's like 4 times the buoyancy of that. It's an insane gas. So anyway, Zeppelin creates these enormous dirigibles, which basically airships. And what he has to solve is 2 things. You can basically float anything with hydrogen. It's so low density. You can make this thing the size of a cathedral, and they were the size of cathedrals. But you've got to be able to, if you're going to use them to actually go anywhere regularly and accurately, you've got to be able to navigate in the wind. You've got to be able to point this thing in a direction and go there. So you have an engine on it, but also you can see it's got a pointed end. It's got rudders, and it's going to fly a bit like a submarine is travelling underwater. In fact, the physics is exactly the same. So you basically make yourself neutrally buoyant. In this case, you make yourself neutrally buoyant in air. In a submarine, you make yourself neutrally buoyant under a liquid, and then you travel around. And those little boxes on the bottom, that's where the people are. And the rest of it is all just the hydrogen. And so you can appreciate that you really have to make that structure very stiff. Right, it can't bend in the wind and collapse in itself, and that becomes harder and harder to do. But there were new alloys, and in the end, aluminium alloys come along and really solve this problem. And that was the war. This is World War I, where of course the military get hold of it and just start bombing everyone. And then London was bombed, Liège was bombed. In fact, that was the first, I think, bombing of a civilian population by a Zeppelin. But after the war's over, these become the first airline. It really is. It's the first airline ever taking passengers from one city to another. And they circumvent the whole world with a Zeppelin, so-called. They have these regular trips from Paris, Berlin to New York, London to New York. They go down to Brazil and back. And why does that work? Because you can make hydrogen anywhere. So as long as where you go, because you lose it along the way, it leaks. It's very hard to keep hydrogen in. But as long as you can get there and you can make more hydrogen, you can go back. So they go around the world and everyone's very excited. It's only for the rich, it's very expensive. But, and in fact, when they build the Empire State Building, they build it with a Zeppelin port at the top. Yeah, they thought it was so the future that actually you would never go to the ground. You would just live in the sky and you'd get out into a Zeppelin port at the top and you'd go to another high building. And it's just this amazing alternative future we could have had, except for this, which is, of course, there were accidents. This wasn't the first accident, but this is the most famous, the Hindenburg. A very, very important, this is when the Nazis were coming to power, so they were using it as propaganda, and there's something went wrong as it was docking in America, and anyway, the whole thing went up. The amazing thing about this is that there was sort of 106 people on board, including staff. I think 80 of them survived this. I mean, and I try to work out how that can be possible when you see that as flames. I think part of the reason is that it's so lightweight that everything goes up. So you're going down, the heat and all the volatiles are going up. Maybe that's what protects them in the end. And of course, what's crashing down on you is not a lot of stuff. It's mostly gas. Anyway, I don't know. Anyway, so what happens is that hydrogen, in the end, isn't the future of our airships. And as you know, like helium now is, although it doesn't compete economically with heavier than air like flying machines. So we have jet engines now, but they are immensely damaging to the environment. So, it is kind of an interesting question. Actually, we clearly always want to fly, and I think most people probably in this room, if I said to you, you're never allowed to fly again, like I'm afraid you've got some disease, which means you can never fly again. You'd find that actually probably one of the hardest things to bear, maybe. People really don't want to give up flying. It's like it feels like we've kind of moved into a world where it's kind of they'll go vegan, but they won't stop flying. You know what I mean? Like it's something about humans. So I think we're going to do something about flying and make it more sustainable. It's not going to be an easy one. Hydrogen planes are on the cards. It's a tricky gas to control. Whether we'll ever have inflatables flying around the world economically is another question. But I think it's an interesting question to think about. One more gas? One more gas. Okay, noble gases. Okay, so an amazing story. Another amazing story. So of course we're all breathing them in now. We're breathing in xenon and argon and helium a tiny bit. And they're in the air. They're invisible. But we can't taste them. We can't see them. We can't smell them. But particularly we can't do any of those things because they don't react with anything. Like it's not just that we don't have the sensors to do it. They just don't react with anything. And so finding the things in the air that don't react with anything, that's not surprising. It took us so long to discover them because reaction and is how you know something's there. And if it doesn't react with anything, then so these are inert. And the first real hint that there was something strange was this result of the spectroscopy, which happens in the sort of late 19th century. I forgot who does it now. Dan. And have a look. So spectroscopy is like taking light and basically splitting it up using prism, and then you see these lines. And these lines correspond to particular bonds inside and energy transitions. Inside a particular atom. And so you can say, when you look at the sun, for instance, here are all these black lines, and they're absorption lines. And so that means there's a bond, an energy level inside the calcium atom that's, as the light is coming out of the sun towards us, it's being absorbed. So there's calcium in the sun. And there's hydrogen in the sun, and there's oxygen in the sun, and they knew that they could see the lines from the sunlight, and then they could do the experiment in the lab, and they could match the two up. So they could put calcium in a flame, get it spectrograph, look at the spectrograph from the sun, and go, that's definitely calcium, that's definitely hydrogen. Well, it's an amazing thing. So we know what's in the sun without never having to visit it. Hooray! There was a weird line, and everyone was like, what's that? There's nothing we found on Earth that's that new element. But there was a lot of people discovering new elements in the 19th century, and it became a sort of, for every 10 claims, there was only one genuine. So it was everyone was skeptical. It really was. And there's probably something else, and it's probably something we don't understand yet. Anyway, then of course there's Mendeleev's periodic table, this is one of the first versions of it, and this is 1869, and it's like not what we see today, but clearly the idea is there, right? You've got these rows which kind of correspond to the kind of the particular families that go across, and you've got the groups is the valence state. But it doesn't work. Like there is group 8, but group 8 has these transition metals in it. And there is gaps, which is really exciting because this then makes people go out and try and find the elements that fit the gaps. But there aren't the noble gases on there, which are normally group 8, because no one had seen them yet. So when this happens, people start thinking, well, where on this table would they fit if it does exist, and had no real idea. But then this guy, Ernest Rutherford, he gets obsessed with the fact that the table, it's the table, but there are some things that don't quite make sense to him, like the weights of the individual elements. They're not exact multiples of each other. They're slightly discrepant. It really irritates him. So he decides to weigh them all, and he starts with hydrogen. And he starts weighing hydrogen, like weighing a gas. I know. I won't go into it, but it's in the book. It's really interesting how you weigh a gas. Anyway, he weighs hydrogen. He works his way through the table, and he gets to nitrogen, and he goes, "Oh, I'll just get rid of the oxygen from air, and then I'll weigh what's left, and I'll take the water out, and I'll weigh what's left." And he weighs it, and he works out how much an atom of nitrogen should be. And then he thinks, I'll just try another way to make sure it matches. Good scientist. So he gets methane, and he what's he doing actually? Why is he getting methane? I can't remember now. No, he gets hydrogen, and damn. Anyway, you have to read the book. Anyway, he gets another way of making nitrogen chemically, and he gets pure nitrogen. He weighs that, and they don't correspond to each other. And then everyone else just thinks, well, fair enough. Like, it's really hard to weigh a gas. Like, don't beat yourself up, mate. But he doesn't do that. He goes, no, there's something wrong. There's something wrong. Something is in the gas sample of the air that I didn't take out. And so he starts calling it argon. He thinks there's argon, another gas, a hidden gas in the air that no one's ever seen before. Anyway, everyone disbelieves him. He's a great scientist, but they say this is an error. Poor guy. Gone a bit mad. Anyway, but this guy, William Ramsey from UCL, London, yes, he believes him, and he starts doing the similar experiments, and he really goes to town on it. He also concludes that argon must exist. And so they denounce it. They announce it to the world, like, argon's an element. It's completely invisible. It has this weight. We've weighed it. It's a new element. It's got to fit on the periodic table, but you can never find it. You can never chemically react with it because it's inert. And everyone's like, yeah. Chin-chinny. So anyway, then William Ramsey goes off, and he starts to, lots of people write to them and give them advice, and start coming up with sort of weird things that they found, gases that bubble off rocks that doesn't correspond to any other gas. So that he starts explaining them, and he basically uses cryogenics. It's a very clever idea. He basically, the cryogenics techniques are getting really good now, so you can really cool things right down. So he starts cooling air right down, and it all liquefies out. So you get to liquid nitrogen, you get to liquid oxygen, and he keeps cooling. And then with the cool state of the liquid, he then starts to warm it up, and he starts looking at what comes off. And he figures this: the lightest things in it will come off first, and I'll isolate them, and I'll put them in a tube, and I'll do the spectroscopy, and I'll see whether the spectroscopy matches the other stuff we found, i.e. the helium in the sun. And bang on. So he finds helium, they find argon, they find another gas, they put it in a tube, they put an electric charge across it, and instead of it just being a sort of dull spark, it glows bright neon. They've discovered neon, which is an amazing thought. And then krypton and xenon, and in the end, radon. So they discover a whole load of noble gases no one ever known before. Pretty amazing story. Oh, these are the tubes, and they're still at UCL, and yeah. And then of course, everyone's like, "Hey, well done, you're brilliant. What are we going to do with this stuff?" And they're like, "I don't know really. I mean, helium's useful, that's useful." And then of course, a French guy goes, "Hey, I know what we can do. We can make signs out of the neon, and they will really light up our cities." And the first sign is not "Welcome to the fabulous Las Vegas." It's Cinzano in Paris. I think this is 1920s. But the whole neon craze then takes off. Neon lights everywhere, and basically America really takes it to its heart. It really seems to embody modernism in America. This go-getting, garish, futuristic way of thinking about the world. But of course now, the noble gases are used everywhere. Like we use them in lasers, we use them in all of our scientific equipment. We use them in foods. Like argon is used to make anything inert. So it's quite a large set of things, which came from that initial scientist going, they really should weigh the same, which I really like. And here we have this is a good place to end. Here we have what we currently have as the periodic table. And of course, here they are. Look, helium, neon, argon, proton, xenon. And it's such an inspiring story, you know. Like when people say, "Oh, everything's been discovered," it hasn't. I'm sure if we look back in 20 years' time, there'll be things that are in the air we breathe, invisible stuff that we just haven't quite had the right technique, or someone hasn't gone, "Do you know what? I don't really believe that result. I think there's something there." And I think that keeping that alive, that spark of curiosity, I think that's what this, to me, when I look at the periodic table and I see that line, I think, yeah, that's what science is all about. Finding the stuff that's invisible in Earth and actually isolating it and then, celebrating it. And that's what the book's about. So, I won't go into oxygen, but I will say that you have to read the book, and that's one of the best chapters. Anyway, I'll stop there, I think, and then take questions. Ammonia. He reacts with hydrogen and ammonia. Of course, sorry. Yeah. Anyway, sorry.
Ammonia was the one.
It's ammonia, not methane.
Yes.
I don't know why. Ammonia. Yeah, he gets the nitrogen from ammonia. Sorry. Okay.
Questions? Could we have a little bit of light in the lectures, dear sir? So I can see if anybody's waving their hand up. Questions?
Sudden silence. Yes, Tim.
Yes.
What's the gas championship? It's hydrogen seems to be
Right.
company again.
If people, do you remember when fuel cells were definitely going to be the future of cars? That was because they're just so much more energy intensive, and they solved the problem of, so fuel cells, for those who don't know it, so you basically take hydrogen and you take oxygen from the air, so you don't have to carry it around with you. You have a tank of hydrogen in the car, you have oxygen from the air, you put them through, and you basically chemically react them in a structure called a fuel cell, which instead of creating heat, creates electricity. So you generate all your electricity exactly where you want it, and then you have an electric car that's driven by hydrogen, but it's not a battery. There is a battery involved, but it's not a major part of the car. Anyway, this was the future of automotive, because with that amount of hydrogen, even though it's not that energy dense compared to normal fuels, it's energy dense enough to have a range of 500 miles, which most electric cars would just love to have. And so everyone was like, "Oh, it's fuel cells," because everyone wants a 500-mile range, and electric will never get there. And of course, where are we now? Like, electric's king, and it doesn't seem ever that the fuel cell will be a thing in cars. I think people are talking about it for much bigger vehicles, like haulage, massive trucks, because then you really do need these ranges and you need a lot more power. So we still haven't seen them, but yeah. I guess my money is also on, if we want to decarbonise shipping, then hydrogen seems to me to be a good place to start, because a lot of the hydrogen being generated renewably will end up, I think, being at ports, because it's got to be near water. So, but it's interesting, because I don't think it's very hard to predict which way it will all go. But it feels to me hydrogen's got to be part of it. Yeah.
Yes, to go on with hydrogen, I read that Toyota has managed to use hydrogen in internal combustion engines. And so they don't need to create electricity, they use the well-known technology of internal combustion. My question then is, at what temperature is hydrogen burning? Is it sufficiently high or low to function like that?
Yeah, well, I don't know the answer to that. I think one of the problems with hydrogen in that scenario is the power you get from that amount of gas mixed with oxygen, because it's not commensurate with diesel or kerosene. They are very, very impressively high energy fuels, and the hydrogen molecule itself, it's great, it will definitely, but it's not as much as that. So I guess the torque you're going to get from that engine is not going to be as high. Maybe that's okay. I think the other problem with hydrogen in that scenario is the safety situation with leaks, as we've seen. Like, it's a very hard gas to control. And you've got a big tank of it in the back. it's difficult. The other thing is hydrogen moves around in steels like at ease. So because it's the tiny atom, it becomes an interstitial and in brittle steels. So I can imagine that's not something that it might make the engines less, the longevity of the engines. And in fact, that's also the problem with fuel cells. Fuel cells have got a lot of power. They're really cool, but they deteriorate very quickly. So I think it's one thing to demonstrate. It's quite another to get a machine that's reliable that can compete against current technology. Really hard, isn't it? Yeah. Oh, that's all there, but yeah.
Go ahead.
Oh yeah.
I have a question about radon.
Yeah.
Why is it objectionable, and is it in any way useful?
Why is it? What? Sorry.
Objectionable.
Oh, you mean it's radioactive?
Radioactive. Is that
It's radioactive. Yeah, it's radioactive. Yeah, it's big, so it falls apart, and it's so you get quite a lot of radioactive forms of radon. They come out of granite generally, and yeah. Then what happens is it collects in the bottom of houses that are built on granite, and it collects in the basement, and in the process of, you don't know it's there, of course it's inert, and you don't feel the radiation, but if you live there for many, many years, you're exposed to a large amount of radiation, you get cancer. But amazing thing, it's a gas, right? It's heavier than gold. That's crazy. And why is it a gas then? Because these things are all solid, right? But these are not, these are gases. An answer, because it doesn't like to bond to itself even, like it doesn't even want to bond to itself. So forming a solid is like the last thing on its mind. I need freedom. So even though it's heavy, and the energy density calculation you'd seem to think, well, it must form a solid, that'd be the lowest energy state. Its valence just means it doesn't happen.
To what extent did hydrogen, as a means of transport, suffer a serious setback because of COVID? Because in fact the Japanese had intended that the entire transport for the Olympics in Tokyo would be hydrogen based, but of course there was no population, there was no visiting tourists to move around. Yeah. Was that a big letdown for the hydrogen economy?
I haven't heard that that's a big thing. I think basically the Japanese are really into fuel cells. They've got domestic fuel cells in people's homes. I think they have a particular situation in Japan. They import every single drop of oil and gas, so they're very keen to get themselves off that. They have a lot of renewable energy and nuclear energy, so they want to use that. So I think strategically they're very pro-hydrogen. They see it as a solution that's geopolitically important for them. I think it's an expensive solution at the moment. So I think even though they're very gung-ho about it, and of course they make a lot of these fuel cells, so that they wanted to showcase them probably to the world and sell them. But I think everyone else has decided they're too expensive in comparison to the alternatives. That's my take on it at the moment. Right. It's just too expensive. But Japan has a history of innovation, so they could crack it. But fuel cells, they have a real problem with it. I mean, they fall apart really quickly. They're not very reliable, and I think it's very hard to. You have to basically create a fuel cell that's not. Because you've got such a lot of energy kind of being exchanged in a very small space. There's just all sorts of side reactions that happen, and that just kills your fuel cell. And I think the same is true of electric batteries. They are very complicated in terms of the cathode and anode, structures. These very, very complicated to get high energy densities, but they deteriorate quite quickly. So, and you see that in your phone, right? The lithium battery only lasts 2 years, charge discharge, and that basically is entropy at work, basically disordering the cathode and anode structure. So I don't know. There's lots to be done. My particular take on that is how to solve it is to take inspiration from nature. Like, we are a battery in a way, and we last longer than 2 years. And how do we do it? It's not that we don't have exactly the same problems. We have very complex metabolisms for taking oxygen from the air and reacting with sugars in our body to get our energy. And we have all sorts of side reactions, exactly the same problem, right? But how have we managed to solve it? We have all sorts of self-healing mechanisms. We capture radicals and we get rid of them. And so a lot of our metabolism is not sort of based on the efficiency of how much power out it is actually keeping a whole metabolism alive. And we don't do that in engineering. Generally, what we do is we try and get the biggest power we can, and if it dies in 2 years, so be it. We'll make a new one. But that's really unsustainable too. So in a way, I feel like we should start thinking about you should use some of the power to reorder your electrodes, and that would be like almost like a living battery then, right? But I think that's the way forward. I take it.
Other questions? If not, you have an opportunity to ask one. Yes.
Yeah.
Sure.
You were talking about batteries. I have no idea of science at all. I'm a complete novice here, so I apologise for more learning people here. But you were saying about batteries and how they run down and everything. As a modern day question, when you charge your telephone, should you let the battery run down entirely? Or can you plug it in any time? Because my husband is always very angry with me about this issue.
Yes.
So I thought I'd ask a scientist.
So modern batteries are designed to be able to be charged at any point. So I think, but it was really true of earlier versions that that you would kill the lifetime if you didn't let them run down. So that, but it's true that it probably is true that the fewer cycles you do, the less damage you have. So if you think about it, if you use if you just charged up your battery and you let it go for longer, then that whole anode cathode structure has had one charge and then it's running down. So it could be that actually it will keep going for longer if you just use that juice for longer. Do you see what I mean? It could be true that the battery will last longer, but it won't kill the battery in the way it used to. They used to it meant that the total charge was much smaller. You could never get to full charge in the old days, but you can now. But it still may affect the lifetime. Yeah. You can both do it. Your different ways.
There we are, thank you.
Yeah.
One last one, yes.
It's a silly question, I'm a non-scientist, but with space exploration, is it likely that Elon Musk will cause us to discover more gases out there in the universe than the ones that we haven't ever seen here or experienced here? And will Elon Musk have a gas named after him that we will have to learn?
God help us.
Yes.
Essentially from now.
Okay. No, it's not a silly question. I think it's a good question. So these are the elements that we know exist, and it's sort of not conceivable that there'd be a new one sort of in here somewhere, because that's the kind of, we've kind of done exhaustive searches and there's a logic to this, and it's probably not going to be one down here. But people do say there's an island of stability down here. So as you go down, these are getting heavier and heavier and heavier. So uranium is, where is uranium? There it is, 92. Uranium is radioactive because it's so many protons are packed into the nucleus, and they don't really like being next to each other. It's just too crowded, and they keep falling apart. That's what radioactivity is. So the heavier the atoms get, the more radioactive they get in general. That's why radon is also radioactive. And so people, when they discover these ones down here, it's only tiny, like a millisecond that ever exists, and they're usually in nuclear reactors and usually in Russia. And although that one was obviously Lawrence Livermore Centre, but so people sort of think, well, there can't be any other atoms down here, and anyway, there wouldn't be gases because they'd be heavy, let's say. But other people say, no, there's an island of stability, which we haven't even found, and it's over here somewhere. And I don't know the answer to that. Then there's most gases which aren't elements; they are actually combinations. So carbon dioxide. So they're combinations of all those things. And I guess we'd feel like you could have a gas we've never seen before because it's in particular pressure and temperature and combination in some planet. And that's totally possible. And it might have some really interesting properties, maybe even some lifelike properties or life-giving properties. So that bit of it, I think, is much more likely. Not that we get a new element, but that we get a new gas or combination on Titan or somewhere, because we keep flying to these places and putting down probes, and the probes are getting more and more sophisticated. So yes, answer. Oh, will it be named after him? Hope not. I hope not. But that's because I find him a bit annoying. But that,